and today we want to work on the vector functions. Those are basically your curves, which are function of one variable. So the way we're going to look at it is we have x, y, and z. X depends on parameter t, y depends on parameter t, and z depends on parameter t. So in a sense, you may be considered that as position particle in three-dimensional space. And parameter t, you can treat that as a time. So in a particular instant, particle will be here, then in a particular time it will be there. And if you try to describe its movement, you're going to get curve, one-dimensional curve in three-dimensional space. Okay. So vector function. So what we have is vector, and that vector we can treat it as functional parameter for x, functional parameter for y, and functional parameter for h. In other words, it's f of t times I plus g of t times j plus h of t times k. Okay. So that is our vector function. We can try to start working with it the same way as you were doing that in some say middle school. Say if you want to get a graph of something, what you do plot points, and then you connect them by something smooth, something like that. So let's try, for example. If we have a vector function given to us by 4 cosine of t times I plus 3 sine of t times j plus 5t times k. Okay, find. So what you want to find out is, say, what will be the position of a particle described by that vector function when time equals to pi over 2. Where in the space is it going to be located? We'll do our regular stuff. We'll substitute pi over 2 for t, and we're going to get a vector. Okay, so that will be position of a particle. Cosine of pi over 2 is 4. So I should put 0. I should put 0 here and 3 here. So basically all that you have to do, just substitute. And if needed, we'll figure out what kind of curve that is. For example, if you carefully look at this one, you see 4 cosine and 3 sine. So that kind of suggests that we will have ellipse, and then 5t for z, which means your z is going to be shooting up faster and faster. So you'll get like firstly something, if you look from above, you will have something which will move along the ellipse and it's shooting upward. You know, we'll try to discuss. Graphing is not easy. I mean, the functions will be difficult really quickly. That's a bad thing. Good thing, differentiation and integration will go straightforward. For example, if I want to find the derivative of a function, a vector function with respect to t, all what I have to do is take derivative of x coordinate, y coordinate, z coordinate separately, put I, j, and k in it if I want, or put them and put commas in between, put them in that parentheses. Okay, so for example, here, derivative of cosine is negative sign. Keep I. Derivative of cosine, sine is cosine. If j, derivative of 5t is 5. So taking derivatives as easy as it were in calculus 1. So if you're good with derivatives, all what you have to do is just do them by coordinates. Same is true for doing antiderivatives. Again, we'll do the same thing. We'll do it by coordinates. Okay, and that will be straightforward. So I'm going to put those here. So integration and differentiation of a vector function is kind of straightforward. You do it by coordinates and it should not be too bad. And I put those here, assuming it should not be too difficult to calculate those integrals. But one of application of derivatives, you remember, is tangent line. So let's do tangent line. Creation of a tangent line to that curve at t equals to pi over 2. Let's see. To get equation of a line, we need to have two pieces of information. We need to have vector, direction, and we also need to point. Point we already know. Point we already know. We already calculate point in our first part. 0, 3, and 5 pi over 2. Right? Okay. Now, if you want to find vector, then essentially that's the same thing as we did in calculus 1. To find slope, you take the derivative and plug in a given point. We're doing exactly the same here. We take the derivative, which you already know, and plug in given instance of t. So vector, tangent vector is going to be the derivative which we found in the part somewhere here. And we're going to substitute pi over 2 into that expression. So we take -4 sine t, 3 cosine t, and 5. And we're going to substitute pi over 2 here. Vector -4, 0, 5. And as soon as we know vector, no point, she'll be able to write down equation of a line. So go ahead and write down parametric equation of a line. I'll catch up on you in a second. Point. Write vector. Multiply vector by t. If we want to be careful, maybe we want to avoid t because t is kind of taken and it's already parameter for initial original curve. So maybe you want to use like different letter and say s. Because we don't want to get confused this parameter with parameter of original vector function. Just to play safe. And that's going to be answer for you. Then we'll move on. So one more time, derivatives, integrals, and I also guess limits. They all be done by coordinates. So we'll be doing them by coordinates. I'll be doing them by coordinates. So derivatives, integral, and limits basically is going to be your calculus 1, but you will have to maybe calculus 2 for integrals, and you will have to do it derivative of x coordinate, derivative of y coordinate, derivative of z coordinate. Same with integral of x, y, of z, and the limits, the limit of a first, limit of a second, limit of a third coordinate. Okay, I'll do a couple of easy ones, maybe. X equals to 4 cosine t, y equals to 4 sine t, z equals to 0. That is, can you recognize the curve? So z equals to 0, z equals to constant. For now, we can don't bother about it much. 4 cosine t, 4 sine t. So you realize that is x squared plus y squared equals to number, right? Equals to 16. Do we see that? Sine squared plus cosine squared, you know immediately that's 1, right? And you multiply everything by 16, so we're going to get 16 sine squared t plus 16 cosine squared t equals to 16. And that is 4 sine t squared plus 4 cosine t squared equals to 16. So x squared plus y squared equals to 4. So that is it. If needed, go ahead and write down the explanation of what was the circle. So x and y will be the circle, and z stays constant, z equals to 0. So what's happening is z equals to 0 is plane. So on the ground floor, when height equals to 0, on xy plane, we have circle of radius, okay, on the plane. Z equals to 0, xy plane. Circle of radius. If you like, you also might mention center. X equals to 5 cosine t, y equals to 0, z equals to 3 sine t. Describe curve. Can you describe this curve? So if I start the explanation, we'll say on a plane, y equals to 0. So y equals to 0 means y disappears, and we have actually only two variables which are changing x and z. So xz plane. It is. And can you recognize what kind of curve is this one? If you just for now just ignore that part which says y equals to 0. Now you can ignore it because it's constant. It's taken care of by saying plane y equals to 0. Do you see an ellipse? So it kind of reminds you about circle, but it's a bit stretched. So that's ellipse. So it's essentially cosine squared plus sine squared equals to 1 in terms of x and y, but you'll have like some coefficients which will stretch it a little bit. So x equals to sine t, y equals to cosine t, z equals to cosine of t. This one is actually difficult. So if you look at on it from above when and z-axis is just like through z-axis, then projection on xy plane is a circle. So if you look from above and you put a shadow of what is happening, that's a circle, because you have x equals to sine, y equals to cosine. And then what z does, z goes up and down, up and down, up and down. You have at, so it does that up and down, so it will do what? 8 complete circles. Just imagine. From xy plane, when you look from above, then you see like circle, right? When you look from above. You see circle. Now, if you look at what is happening for z with time, z with time, that is your cosine function. So it goes like this, right? Cosine function. So it should do was 8 full rotations, right? Because 80. Now, what you do with basically you take this part, which is here, and try to align it on top of this guy. So can you imagine what you're going to see? I'll try to sketch what might be happening. Picture will be probably pretty bad. So inside of cylinder, just imagine on the, so you kind of have your cylinder, right? Somebody suggested to do cylinder. So just imagine cylinder, right? And on the side of cylinder, what you're trying to do, you want to inscribe on the side of cylinder, going up and down, up and down, up and down, and all the way through, right? But you're doing it on one side of cylinder. Do you see that? And that's the curve we are talking about. And then you just pull only that curve, right? Now, I don't know how it's going to. Yeah, probably bad picture. Basically what I'm trying to do is, how are we going to call it? It should remind you maybe something like a crown. And essentially, again, that's this piece. That's only this we're interested in. So you inscribe it or cut it on that cylinder. Okay. So that's the curve we're talking about. So as you guess, it's really easy to get confusion and difficult curves really quick, really easy. X equals to cosine t, y equals to sine t, z equals to t. So what is happening? That's essentially a circle, but you stretch circle, kind of raising it from x, y. Okay. So do you see, like, you start in the bottom on x, y planes? Let me try to. Let's see if I will succeed in graphing. So what you do, you kind of draw in your circle, but at the same time, your circle going upward, right? So kind of circlish, but it's going upward. So we start at x equals to 1, and y equals to 0, and z equals to 0. Then it starts going upward. Okay. And if you remember names of this object, it's going to be called head.